Welcome back to the deep dive. Last time, we started peeling back the curtain on the invisible world of everyday radiation. We look at some pretty surprising sources, bananas, the actual walls of our homes. And I think for a lot of us, it really shifted how we think about it.
Absolutely. It showed radiation isn't just this distant, abstract thing. It's constant. Often benign, but definitely pervasive.
Right. More pervasive than you'd probably guess.
And that first look, while, insightful, it was really just scratching the surface, just the beginning.
Yeah.
Our sources show there are so many more subtle, intricate, and frankly, pretty surprising ways radiation interacts with our lives.
Yeah.
Daily. We only just started.
Okay, so for this deep dive, we're going further then.
Exactly.
Taking people deeper. We want to uncover more specific sources, maybe some counterintuitive ones that are closer than you think.
Right. Building on what we learned, but definitely not repeating ourselves.
No, this isn't just adding more facts to the list. It's about deepening the perspective, maybe challenging some assumptions, getting a more granular view.
Our mission today, really, is to shed light on the whole spectrum, from the totally benign, unavoidable background stuff
Okay.
to sources that, while maybe still safe, show some fascinating biology or geology at work. And then, touch on instances where radiation is genuinely a hazard.
Right, getting that balance.
The goal is to give you an even better framework for discernment, a truly informed awareness. We're hoping for more of those aha moments, connecting things you might not have thought were related.
Yeah, ultimately we want you to feel empowered, looking at your environment with a new lens, making the invisible a bit more tangible and maybe less scary.
Knowledge really does help dissipate fear, doesn't it?
It does. So let's jump right in. Let's continue our journey into this unseen radiance that, well, shapes your daily life. Okay, let's start right at home, like really close to home. Your own body. We mentioned briefly last time that we all have these natural radioactive isotopes inside us, potassium-40, carbon-14. But I think for many people that's still kind of abstract.
It is, yeah.
How much are we really talking about? Can we actually put a number on this personal glow?
The personal glow. I like that. And yes, we can. It's a great question because numbers make it concrete, right?
Exactly.
So our sources show that if you were just lying in bed doing nothing strenuous,
Okay. My favorite activity.
your body's own natural radioactivity contributes about 0.3 microsieverts per hour to your immediate surroundings.
0.3 microsieverts per hour just lying there?
It's just lying there. And a microsievert, remember, is that unit measuring the effective radiation dose.
Yeah.
It considers the type of radiation and how sensitive different tissues are.
Okay.
So this 0.3 isn't just theory. It's measurable, continuous. It's the direct result of isotopes decaying inside you, isotopes that are fundamental to life.
Wow. So if I'm in bed, I am literally a tiny, constantly emitting radioactive source. That's slightly weird to think about.
It is a bit weird, but perfectly normal.
What are these isotopes actually doing, and why is it continuous?
Well, the main players are potassium-40, K40, and carbon-14, C14. Potassium, is essential. It's an electrolyte.
Right, for nerves, muscles.
Exactly. Fluid balance in every single cell. We have a lot of potassium, and a tiny fixed percentage of all natural potassium is this radioactive K40 isotope. So we carry it with us, always.
And it just decays.
It undergoes beta decay,
Yeah.
emits an electron, turns into stable argon-40. It's happening constantly at a known rate.
Okay. And carbon-14.
C14 is different. It's
Yeah.
made way up in the atmosphere. Cosmic rays hit nitrogen atoms, zap, you get C14.
Oh, right.
It's into CO2, plants breathe it in, we eat the plants, or we eat animals that ate the plants.
So it becomes part of us.
Part of organic molecules, yeah. And it also beta decays back to nitrogen-14. But unlike potassium, which our body regulates tightly because it's essential, C14 levels in us are sort of in balance with the atmosphere while we're alive. Once we die, that intake stops. And the decay is what scientists use for carbon dating.
Fascinating. So we're not just getting zapped from the outside. Our own biology is a source. It's like a built-in background dose.
That's exactly it, an inherent radioactivity. It's why really sensitive detectors like at labs or security checkpoints might pick up a signal from a person.
Even if they haven't been near anything radioactive externally.
Precisely. It defines a baseline. It just underscores that radiation isn't some, alien thing. It's part of the natural processes of life on Earth.
So next time I'm lounging around.
You can contemplate the continuous nuclear reactions happening inside your own cells.
Huh. A testament to the complexity of life, indeed. Okay, so from our bodies to what we put in them. We talked bananas last time, the classic K40 example.
The banana equivalent dose.
Right. But I hear there's another contender, something that takes the crown for food radioactivity, a specific nut.
There is. While bananas are great for illustrating K40, if you want the most radioactive common food, you need to look at Brazil nuts.
Brazil nuts, really? Why them?
Our sources highlight them as having significantly higher levels than other foods, even bananas. And the reason is really interesting. It involves a different element and a unique biological pathway.
Okay, tell me about this pathway. What's so special about Brazil nuts?
The key player here is radium, specifically radium-226 and radium-228.
Not potassium this time.
Nope. Radium is naturally occurring, part of the decay chains of uranium and thorium, which are common in the Earth's crust. And chemically, radium acts a lot like calcium.
Ah, calcium, essential for plants, right?
Exactly. And Brazil nut trees, they grow in the Amazon, often in soils rich in these uranium and thorium series elements. And they have this incredibly efficient root system.
Efficient at what?
Efficient at sucking up what it thinks is calcium. But because radium mimics calcium chemically.
The tree gets tricked.
Pretty much. The root system pulls up radium from the soil very effectively, mistaking it for calcium. Then that radium gets transported and concentrated right into the nut itself.
Wow. So other plants might absorb tiny bits, but the Brazil nut tree is like super good at it.
It has a remarkably effective biological mechanism for it, yes, compared to other plants.
That is a clever trick of nature. So, different element, specific biological uptake. Does this make them, dangerous to eat? Should I stop putting them in my muesli?
No, not at typical consumption levels. The levels are higher than other foods, sure, but still very low in terms of the actual dose you receive.
Okay.
You'd have to eat an absolutely enormous amount, like bags and bags, kilograms, every single day for a long time to get anywhere near a level that could be a health concern.
Phew. Okay. Moderation is key, as always.
Exactly. Enjoy them. They're healthy.
Yeah.
But what it shows us is this incredible diversity in nature. How different elements, including radioactive ones, get concentrated in different places, different organisms.
Right. It broadens the picture beyond just K40. Now we're talking radium bioaccumulation.
Precisely. Specific pathways. It's a richer story.
Okay, from food, let's talk about where we live. We know building materials, bricks, stone, they contribute to background radiation. We covered that. But what about those really sleek, polished surfaces in a lot of modern kitchens? Granite countertops. Are they adding to this unseen radiance in a way we can measure?
Oh, they absolutely can. It's a perfect example of how even decorative choices in our immediate environment are part of this natural radiation landscape.
Because granite is a natural rock, right?
Exactly. It's an igneous rock formed from cooling magma deep underground. And its natural composition includes trace amounts of uranium and thorium.
That primordial stuff again.
The very same. These elements and their decay products, they're locked into the crystal structure of the granite.
So it's not just a pretty surface. It's a tiny piece of the Earth's crust right there in the kitchen. And these elements inside, they're constantly decaying.
That's right. Uranium, thorium. They have incredibly long half-lives, billions of years. As they decay, they emit alpha particles, beta particles, gamma rays. So yes, a granite countertop is a constant, though very low-level, source of radiation.
Is it just the direct radiation? Or is there something else?
Well, there's another aspect, radon gas.
Ah, radon. We know about that from basements.
Right. Radon is a decay product of uranium. While most radon in homes comes up from the soil beneath the house, a small amount can actually emanate or seep out from granite countertops because of the uranium content. Usually this contribution is pretty minor compared to the soil source, but it is there.
So while I'm admiring the pattern, there's this invisible process happening inside it. Can detectors actually pick this up? Like if I had a Geiger counter?
Yes, definitely. A sensitive detector like a Geiger counter would likely show a slightly higher count rate near a granite countertop compared to, say, a laminate one or just the air in the middle of the room.
Interesting. But again, not something to freak out about.
Generally, no. The levels are usually very low, well within the normal range of natural background radiation we experience constantly anyway. The point isn't that granite is dangerous.
Okay.
The point is it's a beautiful illustration of how the materials we choose, the stuff we live with, are fundamentally tied to the planet's natural radioactivity. It takes the idea from the house structure down to specific common features. It's just everywhere in subtle ways.
All right, let's shift gears a bit. I want to unpack something now that I think might genuinely challenge what a lot of us assume about radiation risk.
Okay.
It's a comparison that could really flip your intuition on its head.
I think I know where you're going with this. It's one of those facts that really highlights the gap between public perception and, well, the scientific data.
Lay it on us.
Okay. Our sources present this striking comparison. Spend an entire year living right next door to a nuclear power plant.
Okay, right next door. Fence line neighbor?
Fence line neighbor, yeah. That typically gives you a lower radiation dose than taking just one long-haul international flight.
Wow, okay, wait. Lower dose living next to the nuclear plant for a year than one flight across the Atlantic.
That's generally the case, yes. And it directly confronts a lot of the fear around nuclear energy.
It absolutely does. Because instinctively, most people would say, no way am I living near the plant, I'll take the flight, thanks. So why is this counterintuitive thing true?
It comes down to engineering, strict regulation, and, well, physics. Nuclear plants are built with layer upon layer upon layer of containment.
Right, like Russian dolls of safety.
Kinda, yeah. You got the fuel pellet itself, then the metal tubes therein, the fuel rods, then the massive steel reactor pressure vessel, then the primary containment structure, often huge domes of reinforced concrete and steel, and then the reactor building itself.
Multiple barriers.
Multiple very robust barriers, engineered specifically to keep radioactive materials inside during normal operation. Plus, these places are incredibly heavily regulated.
Constant monitoring.
Constant monitoring, strict dose limits for workers, and the public living nearby. Safety protocols are paramount. The actual dose someone living right nearby gets is tiny, often less than the natural variations in background radiation, and it's meticulously tracked.
Okay, so the plants are designed to contain it. What about the flip side? The flight. Why is that higher? We're not near a reactor up there.
No, but you're much closer to space.
Ah, cosmic radiation.
Exactly. When you're cruising at, say, 35,000 or 40,000 feet, you've got much less of the Earth's atmosphere above you.
Right.
And the atmosphere acts like a natural shield, absorbing a lot of the cosmic radiation coming from the sun in deep space. Less shield means more exposure.
Exposure to what, specifically?
To primary cosmic rays, these are super high-energy particles, and also to the secondary particles created when those primaries smash into the air molecules that are still there. Things like neutrons, protons, muons. They all add to your dose.
So the higher you go, the thinner the shield, the more cosmic rays get through. That's the key.
That is absolutely the key. A single transatlantic flight, for instance, might give you a dose somewhere between maybe 0.03 and 0.08 millisieverts. Remember, a millisievert is 1,000 microsieverts.
Okay, so 30 to 80 microsieverts for one flight and near the plant for a year.
Often less than 0.01 millisieverts, so less than 10 microsieverts for the whole year. Significantly lower than even one flight.
That is staggering.
It is. And for frequent flyers, or pilots and cabin crew, those flight doses really add up over time.
Yeah, you can see how it really forces you to reevaluate where the actual everyday radiation exposures are coming from for most people.
It's a powerful case for looking at the data, not just relying on intuition or fear. Data-driven risk assessment.
Definitely makes you think differently. Okay, now let's circle back slightly. Building on the banana dose and our own internal K40, let's look at another way potassium-40 gets into us, something people often take deliberately for health reasons. Supplements.
Ah, yes.
Yeah.
A perfect extension of the K40 concept, because it reinforces that K40 is just everywhere potassium is.
So potassium supplements are radioactive too?
Ever so slightly, yes.
Why?
By their very nature. The reason is simple. All naturally occurring potassium, doesn't matter if it's in a banana, a potato, spinach, or a potassium chloride pill, contains that small fixed percentage, about 0.0117% of the radioactive isotope K40.
So it's unavoidable. If you're getting potassium, you're getting a tiny bit of K40.
Exactly. K40 is essential, remember, vital for our cells. When you take a potassium supplement, you're just getting more of that vital element and inherently a microscopic, biologically insignificant extra bit of its radioactive isotope comes along for the ride.
And our bodies just handle it.
Our bodies are brilliant at regulating potassium. It's called homeostasis. We keep the levels in our cells pretty constant. If you take in extra, your kidneys generally excrete the excess.
So even if you take a supplement, the total amount of K40 in your body doesn't really build up?
Not significantly, no.
Yeah.
The body maintains its balance. So while you are technically adding K40, your internal dose stays within its normal, healthy range.
So, again, perfectly safe. Just another reminder that natural radioactivity is baked into essential nutrients.
That's the key. It's not contamination. It's an inherent property of an element crucial for life.
Right.
And this example nicely takes the idea from food to supplements showing just how pervasive K40 is. Our biology evolved with it, depends on it.
Okay, we spent a lot of time on the low-level stuff, the background, the unavoidable, often harmless radiation that's just part of being on Earth.
Hmm.
But we absolutely have to acknowledge the other end of the spectrum. Radiation isn't always benign. Some places, some situations involve truly dangerous
This
levels.
is critical for perspective, yes. We
Yeah.
need to see the contrast.
And this is where it gets, well, really sobering.
Indeed. This is where we see the devastating power of uncontrolled, high-level contamination. And our sources bring us back to Chernobyl, decades after the accident.
Decades later. And it's still a major issue.
Oh, yes. Parts of the exclusion zone, even today, register radiation levels thousands of times higher than normal background radiation.
Thousands of times. That's hard to really grasp after talking about microsieverts from bananas. What's causing that still?
When the reactor exploded in '86, it released a huge cloud of radioactive materials. Initially, things like iodine-131 were a big concern, but that decays quickly, half-life of 8 days.
Okay.
The lingering hazard, the stuff causing those high readings now, comes from longer-lived radionuclides, primarily cesium-137 and strontium-90.
And their half-lives are much longer.
Much longer. Cesium-137 is about 30 years. Strontium-90 is around 29 years. So even now, almost 40 years later, roughly half of the cesium-137 and strontium-90 originally deposited is still there.
Wow. And where did it all land?
It got spread by the winds and rain, settling onto the soil, plants, water. Cesium in particular moves around in the environment quite easily. Plants can take it up, so it gets into the food chain.
And strontium.
Strontium acts like calcium chemically. So if it gets ingested, it can end up accumulating in bones.
And these levels aren't even across the whole zone, right? There are hot spots.
Exactly. Fallout wasn't uniform. Wind, rain, terrain. It all led to areas where the contamination is much, much higher than others. The famous red forest, where the pine trees died and turned reddish-brown from the intense radiation right after the accident, is still one of the most contaminated places on Earth.
It's just eerie. Especially because we hear that nature is coming back. Wolves, deer, bears.
It is eerie. And yes, wildlife populations have exploded in the zone, largely because humans left.
So the lack of people is a bigger factor for wildlife than the radiation.
In many ways, yes. It shows how much impact we have through habitat destruction, hunting, farming. But, and this is crucial, but the radiation hazard hasn't vanished.
So the animals are living with it.
They are. And studies show consequences. Animals in the hottest zones have higher mutation rates, weaker immune systems, shorter lifespans, more cataracts. They exist. Populations might even be large, but they're under constant stress from the radiation.
So it's not really healing in the way we might think. It's more like adaptation under duress.
That's a good way to put it. Resilience, yes, but in a fundamentally altered, hazardous environment. It shows the long, long shadow of such a catastrophic release. These isotopes will be there for centuries. It's a permanent mark.
A stark reminder of the power involved and the need for control.
Absolutely. It provides that vital balance. Natural background is one thing. Large-scale, uncontrolled releases are something else entirely. It underscores why safety and regulation in nuclear applications are so non-negotiable.
Okay, let's bring this closer to home again. A much more common exposure, a habit many people have, often without realizing this specific risk factor.
This one is important and often gets lost in the other health warnings.
We're talking about smoking.
We are.
Yeah.
Our sources clearly point out that tobacco plants are rather good at absorbing polonium-210 from the soil.
Polonium-210, another radioactive element.
Yes, a naturally occurring one. It's present in the soil, gets taken up by the tobacco plant, and ends up in the leaves. So when someone smokes...
They're inhaling it, along with the nicotine and tar.
Exactly. They're delivering polonium-210 directly into their lungs. It adds a specific radiation dose on top of all the other chemical damage.
Where does this polonium-210 in the soil come from, and why tobacco?
Polonium-210 is part of that long uranium-238 decay chain we mentioned earlier. It's naturally in the Earth's crust. One major way it gets concentrated for tobacco is through phosphate fertilizers.
Fertilizers?
Yeah, the phosphate rock used to make many common fertilizers. Naturally contains uranium and its decay products, including polonium. The plants absorb it through their roots. Also, tiny radioactive particles, including polonium and its precursor lead-210, can actually stick to the tobacco leaves directly from the air. The leaves have these little sticky hairs, trichomes.
Ah, so it gets on them and in them?
Correct. And then it's inhaled.
Why is polonium-210 such a big deal here compared to, say, the K40 inside us?
Two key reasons. The type of radiation and where it goes.
Yeah.
Polonium-210 mainly emits alpha particles.
Alpha. Okay, what does that mean?
Alpha particles are relatively big and heavy, carrying a double positive charge. They can't travel far. A piece of paper or your skin's outer layer stops them easily. But if an alpha emitter gets inside your body, especially inhaled,
Then it's bad news.
very bad news, because they deposit all their energy in a tiny, localized area. When you inhale Po210 from smoke, these particles lodge in the delicate lining of your airways, your bronchial tubes, your lung tissue.
Right where lung cancer often starts.
Precisely. They blast those specific cells with intense, localized radiation damage. This causes DNA mutations, which can kickstart cancer. It's not like K40, which emits less damaging beta particles and is spread throughout your body. This is a targeted, high-energy hit on vulnerable tissue.
And it adds up over time with every cigarette.
It does. A chronic, cumulative radiation dose directly to the lungs. It's fascinating, in a grim way, how this natural element gets concentrated by farming practices and then delivered so effectively by a human habit.
Just one more reason among so many.
One more very specific radiation-related reason why smoking is so incredibly damaging. Understanding these pathways, natural element, fertilizer, plant uptake, inhalation, really highlights the importance of knowing the full picture of our exposures, both natural and self-inflicted. Hashtag TAFE tag outro.
Wow. Okay, so we have really covered some ground today, haven't we? Another deep dive.
We certainly have.
From the actual measurable glow from your own body in bed to the surprisingly radioactive Brazil nut, the granite on the counter, then flipping that intuition about flying versus living near a nuclear plant.
Right, challenging assumptions.
And then confronting the serious end of the spectrum, the lasting impact of Chernobyl, and the hidden radiation risk in smoking from polonium-210.
We've definitely peeled back more layers, showing how deeply radiation is woven into, well, everything. Often harmless, sometimes surprising, occasionally really dangerous.
And the key really seems to be context, doesn't it? The source, the type, the dose, the pathway.
Exactly. Understanding the specifics, the numbers, the mechanisms. That's what matters. Hopefully this gives you a more sophisticated lens to look at your world, to question assumptions, appreciate the nuance.
Yeah, our hope is definitely that you feel more informed now, more aware, maybe less intimidated by the word radiation. It's not just this one scary thing.
No, it's a constant natural phenomenon, mostly benign, but with specific instances where it becomes a tool, or yes, a clear hazard. This deeper dive is about building that richer mental model.
Moving beyond just fear to actual understanding.
This knowledge empowers you to discern risks better, to see the intricate dance between life and the planet's fundamental energies. And honestly, what's fascinating is realizing how much more there is to learn when you really look closely.
So next time you grab a Brazil nut or you're just relaxing.
You might think about that internal K40 hum.
Or the radium, or the cosmic rays on your next flight. You might just feel a slightly deeper connection to all these invisible energies constantly shaping our world.
And maybe it sparks a bigger thought. You know, if life has evolved and adapted to thrive amidst all this natural radiation, cosmic rays, radioactive elements in the ground and our food, what other fundamental unseen forces are shaping us that we just take for granted?
That's a big question.
It is. And thinking about something specific like the polonium in tobacco, how does knowing that precise mechanism shift how we think about personal choices, public health messages, maybe even how we regulate products that interact with these natural radioactive pathways?
Well, it's definitely something profound to reflect on.